Hello, I'm Rachel Street. I'm an astronomer at LCOGT, where we're building a network of telescopes around the world, and I use these telescopes to discover and characterize new planets around stars other than our Sun. The way I do this is I wait for those planets to pass directly between us and their star. From our perspective, it looks as though the planet crosses the face of the star. Now, we don't actually see the planet because it's too far away. What we see is the light from the star becomes slightly dim for a short period of time, and then it returns to normal brightness. That's called a planetary transit. What I'd like you to do with Agent Exoplanet is help me measure some of the images taken by our telescope and discover and characterize the properties of these planets. The mission brief tells you how we measure the planets and takes you through more details of how the stars dim and how that tells you more about the planet. The way in which we measure the stars is to take a sequence of images during the planet's crossing of the stellar disk. From these data, we build up a light curve by measuring the brightness of the target star in each individual frame. I'm going to start with the planet Coro 2b. Here you can see we've got one of the first frames in our data set. Off to the top left, we've got a finder chart which tells you which star in the field is the target and which we can use as comparison stars. The first thing I've got is a little tag. I'm going to place this on the target star. You'll notice it's given me another tag now. The sky is not completely black. So to measure just the light from the target star itself, we have to subtract the light from the sky. So this second aperture has to go on a background piece of the sky with no stars on it. I think that's good. Now, in order to get a transit, we can't just measure the light from the star. We have to do this in a relative way by comparing the light from the target with the light from other stars in the frame, which we assume to be constant stars. So I'm going to pick this calibration 1 tag, and I'm going to place this on a relatively bright star nearby the target in the field of view. Let's see. I'm going to choose this star. Now, we really want as many calibration stars as possible. Any one of them could be variable, and we want to choose which ones we use later on. So I'm going to try one or two more. Let's choose this one. Okay, so now we've got our calibration stars. Let's click Analyze Image, and the computer will measure the brightness of all of those objects. You can see it's presented me with a series of graphs. These are cross-sections through each of the star's images in two different directions. This tells me whether or not there's a single star in that aperture, and it also tells me whether I've lined up my crosshairs with the center of the object. That's very critical for a good measurement, so let me check. That one looks okay. That one looks good. That one looks good. This one I think is a little bit offset. I'm going to recenter it. And let's analyze image again. Okay, that looks much better. We can now go on to the next image in the data sequence. This image will look almost exactly the same. Because it's taken sequentially from the first, it's slightly separated in time from the original image. This means that it might be slightly offset. The positions of the stars won't be quite the same. So we need to recheck our centering. So it looks like the target's slightly offset. Let me move it. And I'll do the same with the other comparison stars. Okay, click Analyze Image again. Once you're happy with your measurements, you can keep clicking through all of the images in the data sequence. So now we've measured all of our frames, we can compile the data into a light curve. But first of all, we need to look at the light curves for each of our stars and decide whether or not it's a good calibrator. So we're going to classify those light curves. We don't know whether or not the stars in the rest of the field of view are going to be variable themselves or not ahead of time, so we find this out from our analysis. This one looks to me like it's variable in its own right, so we don't want to use it. So looking at this light curve, we can clearly see a dip, which is the transit signal. This one looks like it's a good star to use. So I'm going to click on dip and move on to the next one. And once again we see another dip, so this is another good star to use. So having classified all our calibration stars, we can finally move on to the compiled light curve. And there we see our planetary transit. You can see the star starts off more or less constant and then drops as the planet goes across the face of the star. And then, once the planet moves away, it goes back to its normal brightness. Now we can use this graph to tell us more about the planet. By clicking on this and dragging it over the duration of the transit, we can measure the amplitude. This tells us about the size, the physical size of the planet relative to the physical size of its host star. This graphic at the bottom shows you that. This is a relatively big planet and relatively close in to its host star, much closer in than any of the planets in our solar system. The agent allows you to compare your data with those of other people, and the more you measure, the more precise the measurement becomes.
So in 1992, it had been over 70 years since the discovery of the last planet, which was Pluto. And back in 1992, it hadn't been reclassified as a dwarf planet, so it was still on the planet list. And we knew there were no more planets in our solar system, but we were expecting to find planets around other stars, exoplanets. And we knew exactly how to find them, by looking for the wobble in the motions of the stars themselves. As the planets going around in their orbit, their gravity gently tugs on the star. It's not much because stars are very big and planets are not. It gently tugs on that star to make it swing back and forth as the planets are doing their orbital thing. So all we had to do was stare at a star long enough. Now, we wouldn't see the star wibble wobble left or right. What we're actually looking for is the motion of the star towards us and away from us. As it's coming towards us, that light it's emitting will get blue shifted to higher frequencies. And as it's pulling away from us, it'll get red shifted to lower frequencies. So we're looking for that back and forth motion. Super simple, right? Well, it turns out we're not, at the time, we couldn't get sensitive enough detections of starlight to actually look for this effect. So we thought that finding planets would just be like 5 years out or 10 years out or whatever. But then some teams were investigating pulsars. Now, pulsars are a very special kind of star. They're the leftover core of a massive star. They're actually neutron stars. They're just spinning very, very fast. And as they're spinning fast, they actually emit beams of radiation out of the axes, the poles of these stars. And they can wobble as they spin. So this beam of radiation actually sweeps out a big circle. And if that circle happens to come across the Earth, like a lighthouse, the beam from a lighthouse sweeping across the Earth, we see bleep, bleep, bleep. We see a little flash on the sky in radio, because this is radio emission. And some teams started looking for planets around pulsars, but pulsars are dead stars. Why would a pulsar have a planet? Doesn't matter. Let's look anyway, because who knows? Maybe we'll strike it rich. It turns out we did. Because of that ultra fast, ultra precise rotation of the neutron star, of the pulsar itself, and how regular those flashes are. Remember, when pulsars were first found, we thought there was a small chance it was actually aliens trying to communicate with us, because it was so precise. The time between flashes was so incredibly precise over the course of years or decades. These are incredibly accurate clocks, basically. And if there's a planet around one of these pulsars, it will wobble back and forth. And that frequency of the light passing in front of the Earth, the blink, 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 it will change. It will go faster or it will go slower, depending on where the planet is in that orbit. And so there are a few candidates found, but they were tossed down in the late 80s, early 90s. But in 1992, a team found the one. A clear detection of an exoplanet, a planet orbiting around a star. Not just any star, but a pulsar. The long dead remnant of what used to be a star. So there we go. The first planet ever found was actually around a pulsar. Now, how does a pulsar get a planet? Well, we're not exactly sure. I mean, there's some good ideas out there. Maybe the system started off as two white dwarfs, two cores of regular mass stars. They crashed into each other, became a neutron star, and a bunch of junk was ejected in the process. That junk ended up forming an accretion disk, a disk, and then it ended up forming planets. We don't think the planets were there when the star was just a star, because in the last moments of a star's life, when it enters the red giant phase, it creates planetary nebula that's very gravitationally unstable for any planet. So we don't expect pulsars to, if they do have planets, which they do, the planets around a pulsar, we don't think came with the star originally when the star first formed. Something happened, and there are some halfway decent guesses, I guess, to make that possible. But there you go. The first star. Very clever experiment, I would say, using nature's own precision to look for planets around other stars. Hey, it's me again. I know you just watched a few minutes of me, but who couldn't use a little bit more me? I'm just here to beg you to please subscribe. And if I remember, there's going to be a button like right here where I'm vaguely gesturing so that you can click the button and subscribe, and it's super handy. This is so that you can get the latest updates of all my shows. I mean, that's basically how it works. So if you like what you just saw, you'll get more of it if you subscribe. Super easy.